We start. We were discussing last time the propagation delay. We have introduced the definition, and now we need to make let's say a simple calculation of the propagation delay. We will make an approximate calculation, but at least from the functional point of view, it will provide the correct functional dependencies. So, as I mentioned, we focus on the inverter. And so the circuit we consider is this one. We have a CMOS on top connected to VDD and an NMOS below. And so this is the NMOS, and this is the PMOS. Let's assume this is V in, this is V out, and the inverter, let's assume it drives a second inverter. So let's assume we have a second inverter here with again an NMOS and the PMOS here. And okay, in principle we can have a chain like that. So, what is important to understand here is that what type of load does this second inverter represent for the first inverter? Because basically what we have is the following thing. If you consider the DC current, basically there should be no DC current here, because in this direction, along this direction, you have a gate of a PMOS which is insulated from the channel, and the gate of the NMOS which is also insulated from the channel. So there is no constant DC current flowing in this direction. But what we have is a capacitor, because basically here, if we consider the NMOS, there is a capacitor from the gate to the source, and there is a capacitor from the gate to the drain. In general, if you have two conductors, between them there is always a capacitor. Of course, if you have two parallel plate conductors, you know how to compute the capacitor, but I mean, in general, if you have any general two conductors, between them there is always a capacitor. And in the particular case of the NMOS, basically, if this is the transistor, this is probably something I should like to stress. Let's assume this is the NMOS. This is a longitudinal cross-section drawing. Here you have the gate. Here you have the source, and here you have the drain. And of course, between the gate and the channel, there is a capacitor, which is typically called CG, and is equal to the oxide capacitance per unit area times W times L times the area of the gate. So this is the oxide capacitance per unit area, oxide capacitance per unit area times the area this is the area of the gate, gives us the capacitance between the gate and the channel. Just to add some additional notes, this COX we have already written here. It is the electric constant of the oxide divided by the thickness of the oxide. Okay? Just between parentheses, because this is a concept that we have already discussed. Now, actually, how can we represent this capacitance? This capacitance cannot be represented as a capacitance between the gate and the channel, because there is no direct contact to the channel. We only, if this is the channel, which forms when the transistor is on, we do not have a direct contact to the channel, but we have a contact to the source and a contact to the drain. And so instead of writing this capacitance CG between gate and channel, we divide it into two capacitances. One, a capacitance between the gate and the source, because we have a contact to the source, and then an additional capacitance between the gate and the drain. So this is what we call CGS, and this is what we call CGD. And then we write CG as the sum of CGS plus CGD. So this is why I have, let's say, indicated on this circuit only the two separate capacitances. Of course, if we want to be more specific and indicate that these two capacitances are referred to the NMOS, we should write CGS-N and CGD-N, where this N indicates that we're referring to the NMOS. Now, we can do the same for the PMOS. We have this, which is CGS of the PMOS, and then we have this other capacitance, which is CGD of the PMOS. And again, we know how to compute them. Of course, these two capacitances have to be charged and discharged, because when the voltage Vout, for example, goes from VDD to 0 during a switch of the output, the capacitance CGS-N has a voltage drop from VDD to 0, and therefore has to be discharged. Okay? So actually, from an electrical point of view, the thing that this inverter, the first inverter, has to do is to charge and discharge the capacitance at the input of the second inverter. This is the work that it has to do. Okay? And this is also the reason why it takes some time to do that. Why it cannot be instantaneous, because in order to charge the capacitance, you have to, let's say, you have to push some current for some time, because you have to add a finite charge onto the capacitor. Okay? So, and we are going to compute exactly that time. In addition to that, there is a wire here, which is a metal line, that of course has a capacitance with respect to the external world. So we need to represent this capacitance as a capacitance of the wire. Okay, this W is the wire capacitance, because of course there's a line, a metal line, between one inverter and the other, and in general between the output of one gate and the input of the following gate. So you can observe here, if you look at this in some detail, that all these capacitances have a common node, which is this one. This is the same node, and is connected to the output node. And then have another node, which is sometime the ground, or, for example, in this case, the output of the second inverter. Okay. In addition to that, we also have the capacitances of the first inverter, because of course also here we have the CGDN of the first inverter and this is the CGD of the PMOS of the first inverter. So you see you have a lot of capacitances here. What we do is we consider an equivalent capacitance at the output of the first inverter, which takes into account all the other capacitances which have to be charged by the voltage applied at the output of the first inverter. So we have here one single capacitance, which is called C tot, and is the equivalent capacitance at the output. Actually, it is between the output and ground. Okay. Okay, now how do we compute this equivalent capacitance? Actually, this is a bit more complicated, because if all the other capacitors, the single capacitances, were between the same two nodes, between the output and ground, the equivalent capacitance would be simply the sum of all capacitances, right? But indeed, this is not exactly true, because of course you see that the CGD, the various CGD, are not connected to ground. They are connected here to the output of the second inverter and here to the input of the first inverter. Now, I don't want to, let's say, take some time in explaining exactly what we do here, but the point is that I will give just a brief explanation. The point is that these other capacitances that are connected to the output of the second inverter and to the input of the first one count as twice. So basically this C tot is the capacitance of the wire plus the CGSN plus the CGSP, because these are connected between output and ground, and then we have twice the sum of all the capacitance between gate and drain. And the reason is quite simple, is because when you have a capacitance between the output and ground, one node varies between VDD and 0, but the other stays at 0. When you have a capacitance between gate and drain, when the first node goes between VDD and 0, the second node goes between 0 and VDD. So you have twice the voltage variation on the capacitance, and therefore you have twice the charge variation. So it basically, the same capacitance counts as twice the one between the output and ground. Okay, that is a simple explanation. But the main message of this slide is that we can assume that at the output of an inverter there is a capacitance as a load, which includes the capacitance of everything which is at the output of the inverter, meaning the wire and the other gates that the inverter has to drive. And we can switch the logic gate, the inverter in particular, if we are able to charge and discharge that capacitor. So the smaller the capacitor, the easier is going to be charging and discharging, so the faster we can go. and the more current we can drive at the output, the faster we can go. This is pretty intuitive. Okay? And of course, it is true for the inverter in this particular case, but in general, it's true for any logic gate, because all logic gates are working on the basis of the same operating principle as the inverter. Okay, now we just take this quantity for as an equivalent capacitance, and then let's try to compute the propagation delay. Let me now, let us, for example, calculate the propagation delay between high and low. So this means that the output voltage has to switch from the high level, VDD, to the low level, which is 0. Let's assume this is the input voltage. The input voltage goes between 0 and at some point, let's call it 0, it goes to VDD. Let's assume that the input has an abrupt switch from 0 to VDD. Then what happens at the output voltage? Okay, before 0, the output voltage is high, is at VDD. So this is the initial condition. For t smaller than 0, this is VDD, and this is 0. Sorry. For t smaller than 0, the input is 0, and the output is VDD. Okay? This is what we know. And it is the situation we have represented here. So, at 0 plus, just after the switch, what we have is that, of course, you need to imagine the situation. At 0 plus, the input has switched, but the voltage on the capacitor cannot change. Okay? So what we have is the following thing. Regarding the NMOS, VGS of the NMOS goes to VDD. So VGS, let's drive here the NMOS. Okay, NMOS. VGS is equal to VDD, and VDS is V out, which is the voltage on the capacitor, so it cannot change. So VDS is equal to VDD. In this situation, let's assume that VDD is larger than the threshold voltage, so the transistor is on. And also, in addition to that, VDS is larger than VGS minus VTN. So the NMOS is in saturation. Okay? The PMOS instead is in a different situation because VGS is equal to 0. But of course 0 is larger than the threshold voltage, and therefore the PMOS is off. Okay? So you see the situation. As soon as you switch the input voltage, the NMOS goes in saturation and the PMOS goes off. So what does it mean? It means that essentially this circuit has become a different one. It has become essentially a circuit in which you only have the NMOS, which is conducting, so there is some current in the NMOS, and this NMOS is driving the voltage of the output capacitance down because this current is discharging the C dot. Okay? So basically this current is removing charge from the capacitance and therefore is pushing down the output voltage, which is the voltage on the capacitor. Okay? So we know the value of this current because when the NMOS is in saturation, the current is Kn times VDD, which is the VGS, minus VTN to the power of 2. So we know exactly this current. As you can see, this current is constant. So we are discharging at constant current the capacitor. And you also should know the law that governs the behavior of a capacitor. Considering this sign, you see that when the current is, let's look at the sign. When the current is positive, the voltage on the capacitance decreases because you are discharging the capacitor. And therefore, the derivative of the charge of the capacitor is dV out over dt times C is equal to I with a minus sign. So, because when I with this sign is positive, the derivative of the voltage is negative. Okay, so this is the what does it mean in particular? Since the current is constant, okay, and from this expression we have that also the derivative of the voltage as a function of time is constant, which means that the output voltage is going down with a constant slope. Okay, so the output voltage goes down linearly in time with a constant slope. This is dV out over dt, and it is constant, is equal to I over C. Okay, this is going down with a constant slope. Of course, the higher the slope, the faster the process, but this is obvious. Okay, what exactly is happening here? Is this going to be true forever, or let's say until the complete discharge of the capacitor? Actually not. If you look at this expression, of course the NMOS is in saturation only until this expression is true, but VDS is equal to V out, and VGS minus VTN is a constant because VGS is always equal to VDD. So as you see, when the output voltage goes down, VDS goes down, and at some point this relationship is not true anymore. Okay, so we need to check exactly what happens. Let me just add another slide. When VDS is equal to VGS minus VT, let's say smaller instead of equal, to VGS minus VTN, the NMOS goes in the linear regime. And what's the meaning of this? VDS is equal to Vout, VGS is equal to VDD, and VTN is a constant. So Vout smaller than VTD minus VTN is the condition according to which the NMOS goes in the linear regime. Okay? So let's go back. In order to understand that situation, we have to draw a line here. Which corresponds to VDD minus VTN. So when the output voltage, that is this blue line, Vout, goes here at this point, goes below this point, then we have a change of behavior, because here the NMOS is in saturation, and when this condition is passed, the MOSFET is in the, let me write it here, in the linear regime. What happens in the linear regime? As you remember, in the linear regime, the MOSFET behaves as a resistor. So here you basically have just a resistor in parallel to a capacitor. And what happens then? Nothing particular. When the resistor is in parallel to a capacitor, the capacitor continues to discharge itself through the resistor. The only thing that changes is that in the condition before, when the MOSFET was in saturation, the current was constant. When the MOSFET is in the linear regime, it behaves like a resistor, so the current is no more constant, but is proportional to the voltage. And you know that when you have a capacitor which discharges through a resistor, you have an exponential transient. This is a classic situation. A capacitor discharging through a resistor. You have an exponential which gradually goes to zero. So in this particular case, what you have is that at this point, after a linear behavior, you start to observe something which is exponential going to zero. Okay? So this is the this is what happens if we look at at a simple switch of an inverter in time. Okay? Now, if you consider the definition of propagation delay, you remember we need to check the time at which the input voltage passes through VDD half, and it is this time. It is zero by assumption, by definition at the beginning. And then we have to consider the time at which the output voltage goes to zero. Let's assume it is this one, okay? This is VDD half. So this is the time. And then the distance, the difference between these two instants, is what we have defined as propagation delay. In this case, from high to low, because we are considering the behavior of the output. So basically, in principle, it is simple. We have been able to draw the transient of the output voltage. Once we are able to draw the transient of the output voltage, we can compute, we can measure that time. Okay? That's it. Why it is important? because as you remember, the value of the propagation delay gives us the maximum limit of the clock frequency. And this is true for all digital logic. Now, in order to compute that time, we can make some approximation to make things simpler and to assume that in this whole interval, essentially, the decrease is linear. Because, of course, there is let's say, a smooth variation between the linear behavior and the exponential one. And so at the beginning of the exponential, the behavior is more or less linear. So we don't make a big error if we approximate everything with a line. And it is pretty simple, because basically what we have to do is just to know the slope of the output voltage. We know the variation of the output voltage that we need, and therefore we can compute the time that we need. So the calculation is pretty simple. We need to write that the propagation delay from high to low is equal to the variation of the threshold voltage, the output voltage, delta V out, divided by the derivative. Okay, so I put here the absolute value so that we can compute also the variation of delta V out in only the absolute terms. So we have here VDD half, and here dV out over dt, if you remember, is the current divided by the capacitor. Okay, so the absolute module is that one. So here we have the current divided by the capacitor. So it's an easy calculation. C can go above. We have C times VDD. And then we have 2. The 2 goes below at the denominator. And then we have the current. But the current is equal to Kn times VDD minus Vtn to the power of 2. And that's it. That is the result that I want to discuss. Okay? Because you see, in this case, you can see the dependence of the propagation delay upon a few quantities, upon the voltage, the supply voltage, that is VDD, upon the capacitance, upon some intrinsic qualities of the transistor which are contained in Kn, and in a threshold voltage Vtn. So this is the important part. Let me just add a few things. Of course, this is the propagation delay from high to low. We can also evaluate the propagation delay from low to high. In the transition from low to high, what happens, as you can easily imagine, is that only the P transistor works. The N transistor is off, the P transistor works and pulls up the voltage by simply charging the output capacitor. So if we do the calculation again for the propagation delay from low to high, you can imagine that we obtain a relationship which is more or less identical to this one, with the main difference that instead of having here the quantities of the NMOS, we have the quantities of the PMOS. But essentially the behavior is exactly the same. By the way, I have called this capacitance C tot. Let me use C tot again. Okay? So, and if you remember what I said last time that we met, if the two transistors have the same K and the same Vt, then the propagation delay for the two transitions is the same. And indeed, you can see it from this formula. Okay? If the inverter is balanced, so the two transistors have the same K and the same threshold voltage, we have a balanced propagation delay, which is the best thing we can have in order to maximize the clock frequency. Okay, so let's assume that we are in this condition, and now let's simply evaluate this expression. So remember, the smallest the propagation delay, the highest the frequency clock we can have. So let's consider the impact of the various quantities. Let me just use another line here. So first let me write if Kn is equal to Kp and Vtn Vtn is equal to Vtp, then we have that the TPHL is equal to TPLH, and this is what we want. Okay, the clock frequency must be smaller than something like, let's say, 50 times TPHL plus TPLH. Okay, so 100 times over the average. So let's consider the impact of various quantities. First of all, VDD, the supply voltage. Let's consider the expression here. You know that VDD is in two expressions. We have VDD to the power of 1 at the numerator and VDD to the power of 2 at the denominator. Because of course, from a qualitative point of view, you can see that if you have a higher supply voltage, you need to charge the capacitor more in order to have the switch. But at the same time, you have a current which depends on the square of VDD. So you have much higher current. And in the end, you can see that if you have a higher VDD, the propagation delay becomes smaller because the denominator counts more than the numerator because you have a power of 2. Okay? So, and this is an important thing to understand. If VDD, let's indicate the qualitative dependence in this way. If VDD increases, then TP in general, let's write TP the single TP, both the TP decreases and F clock can increase. So one simple way to increase the performance of a digital integrated circuit is to increase the supply voltage. Okay, and yeah. Now the other issue is mu n, the mobility. Now the mobility, in order to understand the mobility, you have to look at this expression where the mobility appears here. The mobility is in Kn. You remember that Kn is mu n times C ox times W over L. And of course, the mobility is down here. This means that if you increase the mobility, again, you can reduce the propagation delay. Okay? And therefore, you can increase the clock frequency. So the dependence, again, is the same. If the mobility goes up, then the propagation delay goes down, and the frequency clock goes up. Well, this is extremely important because let's say, for two reasons. First of all, it's well known that in digital circuits, if you increase the supply voltage, you can increase the speed. And indeed, in many microprocessors now, also on the phone, simply you have these these multiple modes of operation. When you want to go fast, because you have an application which requires more computing power, what you do is you increase the supply voltage to the CPU and you increase the clock frequency. Okay? By increasing the supply voltage and increasing the clock frequency, you can increase the clock frequency and therefore you can go faster. It's because the computing power is simply proportional to the clock frequency. The higher the clock frequency, the more operations you can do per second, and of course, linearly with the clock frequency, you have an increase of performance. So this is something that is routinely used. When when the microprocessor has a lower load, because for example it has, you have fewer calculations to do. For example, the video is stopped and you do not need to process all the video protocol. Then at that time, typically what happens is that the supply voltage to the microprocessor decreases, and at the same time you need to decrease also the clock frequency, because otherwise the microprocessor cannot sustain the clock frequency. You need to keep this true. So when you decrease the supply voltage, you need to decrease the clock frequency to have a correct operation of the device, of the microprocessor. Okay? Now the reason is why you need to reduce the supply voltage. Why would you like to reduce the supply voltage? And we shall see it from a quantity point of view in a few minutes, but the intuitive reason is that you have to decrease the power consumption in order to reduce heat removal problems and to prolong the life of the battery. So in every modern digital system, you need to have this dynamic control of the supply voltage and of the clock frequency of the microprocessor. And this is simply due to this very, very simple expression that we have derived. From a second point of view, if you look at the mobility, that is a good thing, because you see, the mobility is going to improve the performance, essentially at no cost from the point of view of power consumption, as we shall see in detail. And this is the reason why there has been this, let's say, this change of properties of the materials used for the channel at the beginning of 2000, between 2003 and 2005. If you remember, I mentioned to you that some strain has been introduced. This strain, which is putting the silicon in the channel under tensile strain or under compressive strain, has the advantage of modifying the mobility of carriers, particularly to improve the mobility of carriers and therefore to improve the performance. And at that time it was necessary. There was no other way to improve the performance of transistor other than changing the properties of the material. And so we have this tensile strain applied to the end MOSFET in order to improve the mobility of electrons. And then we have this compressive strain applied to silicon in the P MOSFETs in order to improve the mobility of holes. Okay? This is really trying to change the type of materials in order to, the properties of materials in order to improve the mobility and then the device performance. There's an additional thing to look at here, which is the size. So this is interesting here. For example, the length of the transistor. Where does the length of the channel enter here? If you look here in the denominator, basically the length enters here, right? But the length enters also in the numerator, because if you look at the various components of C tot, some of them are not dependent on the transistors. For example, all the wire capacitance is independent of the transistor. But the capacitances, all the other capacitances are gate capacitances. And the gate capacitances are proportional to the length. So this is somewhat proportional to the length. There's a constant part plus a part which is more important, which is proportional to the length and is also proportional to the width of the transistor. Probably I also wrote a note here. Let me see. Maybe here. Yeah, this this CG is proportional to COX times W times L. And of course this is divided in two parts. For simplicity, you can assume that it is really divided into two equal parts. Okay, you cannot be much wrong by assuming that. So all the CGS and CGD are proportional both to W and to L and to COX. And therefore, if you look here, let's write it here. Okay, there is this part. Plus, there is also something that is constant, but it's less important. So, what you should know is that the numerator is proportional to L, the denominator is inversely proportional to L, which means that the propagation delay is proportional to the square of L. And this is extremely important, and it is one of the main reasons for scaling. You see, if you reduce the length, we have that Tp is proportional to L to the power of 2. Okay? And therefore, if L is decreased, then Tp is increased by superlinearly, okay, and then the clock frequency increases superlinearly. Okay? So, if you look at the notes from the previous lecture, you should be able to see that this is true for long transistors. So the situation is not so optimistic. For short transistor, actually the denominator does not depend on L. So we have that P is simply proportional to L because only the numerator depends on L. Okay. If you remember the expression that we wrote for the current in the case of long transistor, there was no L in the denominator, so there is only a linear dependence on L. Okay? But still, from the point of view of the impact that the different things have, this is of course true. So, if we want to improve the performance in terms of computational capability of the logic, we have three different possibilities. We can increase VDD, we can increase mu n, and we can increase L. These are the three possibilities we have. What about the other factors? Well, you can consider here, you can see it pretty easily that, for example, W has no effect because it is both at the denominator and at the numerator, and also COX has no effect because it's both at the numerator and at the denominator. Okay? So, in practice, this is an approximate expression because there are also other factors, but I mean, you have the idea. The other quantities have no particular effect. The only quantity here that can have an effect that we have not yet mentioned is Vtn, because you see here that if you decrease Vtn, the lower is Vtn, the higher is the denominator, and therefore the smaller is the propagation delay. So one could think that it is possible also to work on Vtn. This is not really true. in practice, because actually VTN, indeed VTN can be a problem, because I just can anticipate something that we will discuss in a few minutes, but the point is that if we decrease VTN, power consumption increases too much, and therefore it's not advisable to do that. So we cannot play that much with VTN. Okay. Okay, I think we can have a break.